So solutions we've already talked about a little bit because we've talked about homogeneous mixtures, and we've also talked about molarity, concentration. So we've covered a little bit of this already, but we do have a couple. It's kind of a smaller unit that we're going to do, looking at some other factors that are very important going forward that we understand about solutions. So obviously you want to write down these notes as we go. The graph that you'll see at the bottom of the screen, I'll show you the rest of it in just a minute, and you can do your best to sort of roughly copy it down. But I want to talk about these definitions first. First of all, a solution is just a homogeneous mixture of two or more substances. So homogeneous just basically means, you can't see the different components. If you recall that from back in August, we talked about that for the first time. So a solute is a substance that's dissolved, so the salt in salt water, for example. Solvent is the thing that does the dissolving, like water. Solubility is a measure of how many grams of solute can be dissolved per 100 grams of solvent at a given temperature. For solids, solubility tends to go up with temperature increase, and that's just because the particles are moving around faster. So it allows those water molecules to interact with the ions or molecules or whatever it is that's being pulled apart in the solute. Now, I'll show you the graph here of solubility. This is just three solids. Solubility measured in, you can see there, grams of solute per 100 cubic centimeters of water, which just means milliliters. We usually say milliliters. So you can see there that there's a direct relationship for all three of these with temperature. As temperature rises, the amount that you're able to dissolve in 100 grams of water rises. And you can obviously see that the most soluble one here is potassium iodide. We often think of sodium chloride as being extremely soluble in water, but it is kind of limited compared to these other two, particularly at higher temperatures. And you can see that the relationship between temperature and solubility for sodium chloride isn't as pronounced. It goes up a little bit with temperature, but not a lot. You might notice that you can dissolve more salt in boiling water when you're, cooking, but it's actually not a whole lot more. It does dissolve faster at a higher temperature, but you're not necessarily going to be able to dissolve a whole lot more sodium chloride. But there is a direct relationship there. So there we see, for gases, it works in the opposite direction. So again, and these graphs don't have to be written, perfectly, just to kind of get a rough idea of the relationship. And you don't have to include all the gases that I have here in this graph. Maybe sketch oxygen and nitrogen would be good enough. It's the same graph, solubility. It's measured in milligrams per 100 grams of water, just because gases are less soluble by mass than solids are, so we have to use a smaller unit for the solute mass. And the relationship is just the opposite. So at higher temperatures, we actually have less dissolved gas, which, if you've ever noticed, like at school sometimes when you get water out of the tap in the classroom, it'll be cloudy, and that's because the cold water in the pipes, as it comes up through to the faucet, is actually being warmed by probably the cold water pipe is being warmed by the warm water pipe that's traveling next to, and the dissolved nitrogen and oxygen and all that stuff is coming out of solution, because at higher temperatures, it might be at 10 degrees outside, and then it comes into the school, comes up through the pipes and warms up to 25 degrees. Well, you can't have as much dissolved oxygen at 25 degrees as you can at 10 degrees Celsius, so it's going to become undissolved and cloudy. It's also the reason that certain species like fish and insects can only survive in really cold water, rivers and ocean water if the temperature is cold enough, because there's only so much dissolved gas in that water, particularly oxygen for animals. And things like trout don't really live in the wild in Missouri unless they're released, because Missouri streams are just not that cold year round, and so therefore in the summertime in the Merrimack River or Current River or wherever, the temperatures get a little bit too high for them to have enough dissolved gas, enough dissolved oxygen to breathe. Whereas in Colorado, Montana, places like that, you can have trout living year-round because, and living naturally because trout need more oxygen, and that's available in the colder waters in the mountains. It's also the reason that thermal pollution is an issue. So you can actually have, factories and industrial processes dumping, pure water into streams and rivers, and it causes a negative impact biologically because if you warm up that water, the river water, even with clean, pure water, you're going to cause gases to become undissolved. And if carbon dioxide comes out of the water, then plants underwater can't live. If oxygen comes out of the water, then animals underwater can't live, etc. So it actually can be an issue, but the relationship is negative. The gas particles at higher temperatures are more likely to find each other and bubble up, and those bubbles then float to the surface and are released. Kind of like when you open a soda, except that's happening due to pressure change versus a temperature change. So solutions can actually be made of a couple different combinations. The most common, solid dissolved in liquid, like salt water, liquid dissolved in liquid, like alcohol dissolved in water, is an interesting one because actually alcohol and water are completely dissolvable in one another. So you can have a mixture that is 1% alcohol and 99% water, or it can be the other way around, and it kind of switches which one is the solvent and which one is the solute. Or they can be 50-50, in which case it's kind of arbitrary to say which one's the solvent and which one's the solute, because whichever one you have more of, you call the solvent. Gas, we just talked about, dissolved in like the oxygen found in water. Gas and gas, so actually our atmosphere is a solution of oxygen, nitrogen, carbon dioxide, water vapor, all kinds of fun stuff. Solid and solid, so if you have 18 karat gold, 14 karat gold, stainless steel, steel itself, brass, bronze, those are all alloys that are solid mixtures, and they're homogeneous, so we call them solutions. Water is a very important point here. Water is considered the universal solvent because in chemistry especially, it's what we're mostly going to be using. And that's because water can not only dissolve ionic compounds, because it can dissolve ionic compounds by pulling ions apart, but it can also dissolve polar covalent compounds and even some nonpolar gases like oxygen and nitrogen. Okay, so what does the dissolving process look like? And we've kind of talked about this before. But essentially, when you put an ionic crystal into water, the water molecules, because of their polarity, the positive and negative ends, the water molecules are going to be attracted in a very specific way to the positive ion, the cation, like sodium, and then in the opposite way to the negative ion, the chloride. And it's going to pull the crystal apart, and this would be the way you would write that reaction. Now the process is reversible, so once you get enough of these hydrated or dissolved ions, the opposite can happen. So you might have some ions being pulled off of the crystal here, and then over here on the other side you might have some ions that are being attached to the crystal. So once you have, at first when you put the salt into the water, you're going to have a lot more of the dissolving than you are the crystallization. And so eventually, it's going to all the solute's going to be dissolved because you have one process, which would be the crystallization up here, happening a lot faster than the reverse process, which would be the dissolving up here is happening a lot faster than the crystallization, which is shown down here. I don't have a picture of crystallization, but it's just the opposite, arrows going in the other direction. So eventually, it becomes all dissolved. Eventually, though, if we add enough solute, it reaches equilibrium, and equilibrium is a very important term we're going to be using not only in this unit but in the next few units. It just means a balance between two opposite processes. So if you're spending money as fast as you're making money, your bank account is going to be at equilibrium. If you're consuming calories at the same rate you're burning calories, your weight is going to be at equilibrium. It's essentially just you stay the same because these two opposite processes are still happening, but they're happening at the same rate. So if I have crystallization and dissolving happening at the same rate, I'm going to be at equilibrium. And what that means is you're going to have some undissolved solid remaining sort of like some salt crystals sitting at the bottom of the glass if you're dissolving salt in water in a glass, because the crystallization is happening, the dissolving is happening, but they're happening at the same rate. That won't happen unless you put in enough salt, though. Okay, so the solution at that point is considered to be saturated. So a saturated solution just means that you can't dissolve any more salt. So if I have added enough salt to a glass of water, the remaining salt is just going to sit there at the bottom undissolved. Now there's still dissolving happening, but like I said earlier, it's happening at the same rate as crystallization or recrystallization, whatever you want to call it. So therefore, the total amount of dissolved solid remains constant. You could also say that the concentration of the solution remains constant. No matter how much salt I continue to add, the solution, stays the same molarity because we're not increasing the amount that's dissolved. An unsaturated solution just simply means the opposite. So no more could be added, or I'm sorry, more could be added. So an unsaturated solution is one where essentially it's all dissolved, and you don't have crystallization happening anymore because it's all in solution, and there's plenty of water there to surround and hydrate all of those ions. A supersaturated solution is very unique because this means that the solution contains more dissolved solute than it should at any temperature. So let me kind of show you how this happens, and you can sketch this out if you want to. This little drawing. But basically what we have here is, at this given temperature, we're going to say that a maximum of 36 grams of sodium chloride will dissolve in 100 milliliters of water, or 100 grams of water. And so if you put in 30 into 100 grams of water, remember that water is 1 gram per milliliter, so that's why I'm saying grams and milliliters interchangeably for water. If I put in 30 grams, it's all going to dissolve, and this water could dissolve more. So therefore, you don't see any solid sitting at the bottom. If I put in 40 and stir it up or just give it time, I'm going to have 36 grams of it dissolve and 4 left over at the bottom undissolved. Now there's still, as I said, dissolving happening. We have some crystallization happening at the same rate though, so that 4 gram number remains constant. So this is an unsaturated solution because we could throw more in there. This is saturated because we couldn't, and the evidence is that we have some solid sitting at the bottom, and no matter how much I stir it, it's not, that 4 grams is going to remain there at the bottom. Now to get a supersaturated solution, this is kind of a unique thing that we can sort of force to happen. If I were to take this glass and heat it up, put it on a hot plate and warm it up, and that extra 4 grams dissolves, and then I turn the hot plate off and leave it alone for a little while, and it cools back down to the temperature that it was at, let's say 25 Celsius room temperature. Most of the time, those 4 grams of solid are going to recrystallize and fall down to the bottom of the glass. But sometimes a very unique thing happens, and that is that even though we still have that 40 grams in there, that 4 grams does not come back out of solution. So even though we've reached 25 degrees Celsius, at which only 36 grams should be dissolved, the 40 grams, all 40 grams, stays dissolved at that temperature. That's what makes a supersaturated solution. And then we're going to get a chance to take a look at that in class next time.